Hey everyone, I hope you're doing well today. In this video, let's talk about some important properties of logarithms. Now, the word logarithms, or log for short, seems like kind of a random word, but it comes from two ancient Greek words, logos, which means ratio or proportion, and arithmos, which just means number. In this video, I'm going to start by talking about inverse properties, where I'll try to show you why log base b of b to the a power is just equal to a, and b to the log base b of a power is also equal to a. At some point in the video, I'll also talk about the change of base formula, where log base c of a is equal to log base b of a over log base b of c, where b is any value except for 0. Keep in mind that for any of these properties, b won't equal 0. Bringing it back to properties, we'll also talk about the product property, where we'll talk about why log base b of m times n is the same thing as log base b of m plus log base b of n. Another property we'll talk about is the quotient property, where we see that log base b of m over n, or m divided by n, is equal to log base b of m minus log base b of n. And the final property we'll be discussing in this video is the power property, where we'll talk about why log base b of m to the n power is just equal to n times log base b of m. Now, if you think you're going to find this video helpful in any way, or you just want to support this channel since it's a non-profit to help students receive free tutoring, I'd really appreciate it if you could like this video, consider subscribing, and leave a positive comment. By doing so, you help the YouTube algorithm spread this video to other students who might find value in this as well. And in return, by subscribing, liking, and commenting for the YouTube algorithm, I can continue going over mathematical algorithms. And without further ado, I encourage you to grab some paper, something to write with, and let's do some math together. Now, before we get into the properties I promised we'd cover, let me go over some background information first. To start off, we're going to review what inverse functions are for just linear functions so we can apply that concept to logarithmic and exponential ones. Imagine we have the function f of x is equal to 2x plus 5. To find the inverse of this function, we're going to swap out f of x and just say that's equal to y, and say y is equal to 2x plus 5. When finding the inverse, the next thing to do is swap x and y, so we'll have x is equal to 2y plus 5. And to find the inverse, we now just have to isolate y. Subtracting 5 from both sides, we can write that 2y is equal to x minus 5, and dividing both sides by 2, we can say that y is equal to 1/2 x minus 5/2. And at the very end, we can specify that this y is the inverse, so we can say that f to the negative 1 power of x, or the inverse of the original function, is equal to 1/2 x minus 5/2. This is the inverse. Now let's try to remember how to verify if two functions are actually inverses of each other. Now remember, to verify if f and f inverse are actually inverses of each other, then f of f inverse of x has to just equal x, and f inverse of f of x also has to equal x. If these two statements hold true, then we know that these two functions are indeed inverses of each other. And just to give you a visual on a graph, you can see f of x located here, and f inverse of x located over here. On a graph, you can visually see that they're inverses because they're reflections across this diagonal line f of x equals x. Now let's see how this relates to exponentials, and specifically logarithms. Imagine we have the function f of x is equal to 2 to the x power. To find the inverse of this exponential function, let's change f of x to y and write y is equal to 2 to the x power. Swapping x and y, we can then write x is equal to 2 to the y power. Now this next step might be a little uncomfortable and new for you, but just hang in there with me for a moment. Now to isolate y completely and solve for it, we need to get it down from being the exponent. Seeing that the base of the y is a 2, we're going to take log base 2 of both sides of the equation. One of the interesting things that you'll hopefully understand by the end of this video is that you can take this y and bring it in front of the logarithm and multiply it instead. If that doesn't really make sense right now, I hope it will later when I go over that concept a little bit more. From that, we'll get log base 2 of x is equal to y times log base 2 of 2. Since log base 2 of 2 is equal to 1, we can write that y is equal to log base 2 of x. This particular y represents f inverse of x, and this will be our inverse, log base 2 of x. Now let's verify that f of f inverse of x does actually equal x. Substituting in log base 2 of x in for x, we can now write 2 to the log base 2 of x is equal to x. In a little bit, we'll go over this in more detail, as this is one of the inverse properties. That being said, substituting in f of x in for the x in f inverse of x, we should be able to write log base 2 of 2 to the x power is also equal to x. Hopefully these were good refreshers to remind you how inverse functions work and how we can apply these to inverse properties of logarithms. Let's look at this visually now on a graph. Here's f of x, which is our exponential function, and here's f inverse of x, or our logarithmic function. As you can see here, the domain and range swap for the two functions, and the exponential function has a horizontal asymptote, while the logarithmic function has a vertical asymptote. And just like the linear functions we discussed earlier, we can see that they're reflected across that diagonal line, f of x is equal to x. Now let's look at inverse properties in a little bit more detail. For this first example, let's let a equal 2 and b equal 3, and we can write log base 3 of 3 to the second power is equal to 2. If you were to just go ahead and solve this, we can say that 3 to the second power is 9, so we have log base 3 of 9 is equal to 2. And to write this in a form that's more familiar to you, we can write 3 to the second power is equal to 9. So this verifies for us that the 2 in the exponent is actually just what the whole logarithm simplifies down to. Now let's look at a different example when a is equal to 4 and b is equal to 10. Here's the equation log of 10 to the fourth power is equal to 4. Don't forget, if you don't see a base, it's always going to be a 10 by default. 10 to the fourth power is 10,000, so we can write log base 10 of 10,000 is equal to 4. And to make this a little bit more concrete, we can rewrite it in exponential form and say that 10 to the fourth power does equal 10,000. So far, this checks out. And for good measure, let me show you one more example where a is equal to 3 and b is equal to 5. Given that we have log base 5 of 5 to the third power is equal to 3, let's see how this makes sense. 5 to the third power, or 5 cubed, is equal to 125, so we can write log base 5 of 125 is equal to 3. Since log base 5 of 125 just represents how many 5s multiply to get to 125, we can say 5 to the third power is equal to 125, which is also true. Now let's look at the second inverse property, where b to the log base b of a is equal to a. In his first example, let's let a equal 16 and b equal 4. Writing an equation, we get 4 to the log base 4 of 16 is equal to 16. Just looking at this exponent, log base 4 of 16 is just equal to 2 because 4 times 4 is 16, so there's 2 4s. We can write 4 to the second power, or 4 squared, is equal to 16. Since this is true, we can see that this would just simplify down to 16. Now let's look at this scenario where a is equal to 8 and b is equal to 2. Given the equation 2 to the log base 2 of 8 is equal to 8, let's see if that's true. Log base 2 of 8 is just equal to 3, so we can write 2 to the third power is equal to 8. This seems to check out. And for one final inverse example, let's let a equal 7 and b equal 10. Given that 10 to the log of 7 is equal to 7, let's see if this is true. To solve log of 7, or log base 10 of 7, I'm just going to use a calculator and find out that that is about 0.8451. It turns out that if you raise 10 to this exact decimal, you would get exactly 7. Since I rounded, it'll be approximate though. Now, generalizing this for all other numbers except for when b is equal to 0, when the base of the logarithm matches the base of the exponent, we can just chop down this tree, or this log here, and this a, or the exponent, maybe that's an apple, is going to fall down to the ground, and we just have the a here. For some reason, my mind works a little weird like that. When I think of logs, I think of trees, so maybe it'll help you if you think about just chopping down that tree or that log, and then that apple or the a just comes down. So as long as the base is matched though, this is going to work out each time. And similarly, when you have this pattern where b is the base of the exponent and b is still the base of the logarithm, when you have b to the log base b of a, you can also chop down this tree here, and this a or this apple falls down, and this just simplifies down to a. Just make sure that your b or your bases match. Hopefully, with a few different examples, I've now proven to you why these two inverse properties work. Now let's take a look at the product property. This one states that log base b of m times n is equal to log base b of m plus log base b of n. Let's look at the example of log base 2 of 32. These are some relatively nice numbers because this is just going to equal 5 because 2 to the 5th power is equal to 32. Now to understand this property a little bit better, let's separate the 32 into two factors of 8 and 4. We can rewrite this as log base 2 of 8 times 4. Let's split 32 into two factors of 8 and 4 and try to expand this logarithm. In doing so, the property states that we could write this as log base 2 of 8 plus log base 2 of 4. Now, log base 2 of 8 is just equal to 3, and log base 2 of 4 is equal to 2, and we can verify here that 3 plus 2 does equal 5. Now, while in that example, we broke up 32 into two factors of 8 and 4, imagine you were to break them up into two different factors like 16 and 2. Using the product property, or expanding it into two separate logarithms, we can write log base 2 of 16 plus log base 2 of 2. Log base 2 of 16 is equal to 4, since 2 to the 4th power is equal to 16, and log base 2 of 2 is equal to 1, since 2 to the 1st power is equal to 2. Just like earlier, we can see that 4 plus 1 is the same thing as 3 plus 2, which does indeed equal 5. Now let's look at it from the other direction. Let's start with two separate logarithms and combine them into one using the product property. Given that we have log base 3 of 27 plus log base 3 of 3, let's solve it first and then apply the property. Log base 3 of 27 is equal to 3, since 3 to the 3rd power equals 27, and log base 3 of 3 is equal to 1, since 3 to the 1st power is equal to 3. Adding these two together, we know the answer is going to be 4, but let's try using the property. Using the product property, we should be able to multiply 27 and 3 together to write this as one logarithm and say log base 3 of 81. Because 3 to the 4th power is equal to 81, then log base 3 of 81 is just equal to 4. And this checks out because 3 plus 1 does equal 4. Now let's think of two more factors that also multiply to get 81, like 9 and 9. We could write two separate logarithms like log base 3 of 9 plus log base 3 of 9, and that should equal log base 3 of 81. We already know that log base 3 of 81 is equal to 4, but let's see if the left side works out. Log base 3 of 9 means 3 to the 2nd power equals 9, so this is just equal to 2, and that means that this log base 3 of 9 is also equal to 2. Adding these two 2's together, we do get 4. Generalizing this, we can say that log base z of xy, or x times y, will be equivalent to log base z of x plus log base z of y. As long as we stay away from 0 and negative numbers, we can use any value for x, y, and z. Now let's talk about the quotient property. It states that log base b of m over n, or m divided by n, is equal to log base b of m minus log base b of n. Let's take a look at log base 2 of 64 over 16. Since 16 happens to be a factor of 64, we can simplify this and write log base 2 of 4, and this is equal to 2. Now, while we already know the value of this particular logarithm, let's see how the quotient property comes into play. Apparently, we can rewrite this using two separate logarithms and write log base 2 of 64 minus log base 2 of 16. The numerator goes in the first logarithm, and the denominator goes in the second one. Log base 2 of 64 is equal to 6, since 2 to the 6th power is equal to 64, and log base 2 of 16 is equal to 4, since 2 to the 4th power is equal to 16. Subtracting these two values of 6 and 4, we do indeed get the 2 that we got from the beginning. While we just practiced rewriting one logarithm using the difference of two logarithms, let's take a look at the difference of two logarithms and write one logarithm using the quotient property. Looking at the expression log base 5 of 125 minus log base 5 of 25, we see that log base 5 of 125 is equal to 3, since 5 cubed is equal to 125, and log base 5 of 25 is equal to 2, since 5 squared is equal to 25. Subtracting 3 and 2 together, let's see if we get the same value when we combine the two logarithms. Using the quotient property, we can rewrite the difference of two logarithms with the same base as a quotient and write log base 5 of 125 over 25. Again, the 125 is going to go on top since it's the logarithm that came first, and the 25 is going to go on bottom since it's being subtracted or divided here. Dividing 125 by 25, we can simplify this logarithm to log base 5 of 5, and that's just equal to 1. Since 3 minus 2 was equal to 1 from earlier, this also checks out. Therefore, I think it's safe to say that if we were to generalize and say log base z of x over y, or x divided by y, this is going to always equal log base z of x minus log base z of y. And again, stay away from values that are 0 or negative, or just say positive numbers in general, and this will work out. Now let's talk about the power property. This states that log base b of m to the n power is equal to n times log base b of m. Let's take a look at log base 4 of 64 raised to the 3rd power. Now, if you didn't know about the power property, you would take 64 and raise it to the 3rd power, and you would write log base 4 of 262,144. Since this big number can be rewritten as 4 to the 9th power, we can rewrite this as log base 4 of 4 to the 9th power. Now, using our inverse property, you could rewrite this and say this is equal to 9. However, let's try using the power property to save us a little bit of work here. Remember, the property states that we can take the exponent of a logarithm and put it in front and multiply it by the logarithm instead. The value of this expression should stay the same regardless if 3 is the exponent of 64 or if 3 is being multiplied by log base 4 of 64. Evaluating log base 4 of 64, that's equal to 3 since 4 to the third power is equal to 64, so when we simplify this and write 3 times 3, this does equal 9 and this checks out. Now let's see how we can go backwards using this property. Imagine we have 2 times log base 3 of 81. Evaluating the logarithm, we can say that log base 3 of 81 is equal to 4, since 3 to the fourth power is equal to 81, and simplify this to 2 times 4, and this is equal to 8. Now, using the power property, we should be allowed to take that 2 that's in front of the logarithm and raise 81 to that power. Now let's see if that's true. 81 to the second power is 6,561, so we have log base 3 of 6,561. And it turns out this is just equal to 8 since 3 to the 8th power is equal to 6,561. Using the power property, we were able to take the 2 that was in front of the logarithm and use it as the exponent for 81. To generalize here, we can say that log base z of x to the y power is equivalent to y times log base z of x. Now that we're done talking about the general properties, let's talk about the change of base formula. This formula states that log base c of a is equal to log base b of a divided by log base b of c. Let's take a look at an example of log base 2 of 8. While these numbers work out nicely and this is just equal to 3, since 2 to the third power is equal to 8, let's try to use the change of base formula to understand this a little bit better. According to this formula, we should be able to rewrite this expression as log base b of 8 over log base b of 2. The 8 in the original expression goes in the numerator, while the 2 in the original expression goes in the denominator. The cool thing about this formula is that b can equal any number, as long as it's not equal to 0. To verify that this is true, let's try a couple different values for b and see if it works out. In the case that b is equal to 2, we can write log base 2 of 8 over log base 2 of 2. Log base 2 of 8 is equal to 3, and log base 2 of 2 is equal to 1. This does equal 3 as well. Now to choose a different number, let's say b is equal to 8. We will write log base 8 of 8 over log base 8 of 2. In the numerator, log base 8 of 8 is equal to 1, and in the denominator, log base 8 of 2 is equal to 1/3. Now, if you're a little confused about the denominator, take a look at this. If you were to raise 8 to the 1/3 power, that's the same thing as taking the cube root of 8, and that's equal to 2. Since 8 to the 1/3 power is equal to 2, then log base 8 of 2 is equal to 1/3. 1 over 1 over 3, or 1 divided by 1/3, is just equal to 3. Now here's a third example where b is a different number, like 10. Now in most cases we can just write log of 8 over log of 2, and the 10s that are down there are implied, but I'll write them in there just in case for today. Plugging this into a calculator, log base 10 of 8 is approximately 0.9031, and plugging in log base 10 of 2, or just log of 2 into the calculator, we get about 0.3010. Even though we have these rounded decimals on top and bottom, hopefully you can see that the top decimal is about 3 times larger than the bottom decimal. While these are just 3 examples, you can choose any value for b as long as it's a positive value, and you will also get 3. Now let's try going the other way using this change of base formula. Let's start off with a fraction or a quotient, and then use the change of base formula to combine it into one logarithm. Here we have log base 2 of 32 over log base 2 of 8. Now, before we even apply the formula, let's see what this expression is equal to. In the numerator, log base 2 of 32 is equal to 5, and in the denominator, log base 2 of 8 is equal to 3. The value of this expression is 5/3. Now, since the numerator and denominator have the same base, we can apply the change of base formula and rewrite this as log base 8 of 32. Rewriting this in exponential form, we should be able to say that 8 to some power is equal to 32. Now, to rewrite this equation with the same base, we can rewrite 8 as 2 cubed, or write 2 to the 3x power, and rewriting 32 with the same base as 2, we can write 2 to the 5th power. Since these bases are the same, we can set 3x equal to 5 and divide both sides by 3 to see that x does equal 5/3, which does match what we originally had. Similarly, we should be able to rewrite the original expression but change the base to 4 instead of 2, and this should still work out. Now, rewriting the numerator and denominator into exponential form as 2 separate equations, we can write 4 to some power is equal to 32, and 4 to some power is equal to 8. For the equation on top, we can rewrite the equation as 2 to the 2x power is equal to 2 to the 5th power, so we have the same base. And for the equation on bottom, we can rewrite it as 2 to the 2x power is equal to 2 to the 3rd power. For the equation on top, we can set 2x equal to 5 and divide both sides by 2 and see that x is equal to 5 halves. And for the equation on bottom, we can set 2x equal to 3 and divide both sides by 2 and see that x is equal to 3 halves. Taking the 5 halves we got on top and dividing that by the 3 halves we got on bottom, we can divide these two fractions or multiply by the reciprocal of the second fraction and see that this does also equal 5/3. And generalizing this to other numbers, we have log base y of x is equal to log base z of x divided by log base z of y. Just keep in mind that z can be any base as long as it's not equal to 0, but also remember that it can't be negative because of the domain of logarithmic functions. And that wraps up this video on these different properties of logarithms, including the change of base formula. Now, while I didn't really go into any detailed practice problems in this video, I'll be sure to in a future one, so look out for that. So once again, if you found some value in this video and it helped you understand logarithms better than you did before, I'd really appreciate it if you could help out the channel by giving the video a like, maybe even a comment, and subscribing to the channel. As always, keep up the great work, and I'll see you in the next one.